Hey, this is Brock Lemire's, and in this video I'm going to introduce the concepts of electrical voltage and power. So we have taken a look at kind of the atomic structure of materials and this whole notion that an atom is made up of a nucleus that contains a neutron and proton, or multiple neutrons and protons, and then there's orbiting electrons, and the electrons have a property called charge. And we've also looked at how there are some types of elements that allow electrons to easily move in and out of their outer shell, okay? And this allows electrons to essentially move to other atoms. So all we really need to do at this point is find some way to get these electrons to move, and we will have electrical current. So by nature, they don't automatically move to their neighbors. They need some sort of charge to attract or repel them in order to cause the movement. So if what we need to do is provide a charge across a material in order to encourage these electrons to move. And it does more than encourage. It will actually assert a force on these electrons, and these electrons will then move. Now remember that if we put a positive charge over here and a negative charge over here, the electrons will be attracted to the right, but the holes or the vacancies that they leave will in effect be moving to the left. And so the holes represent positive charge, and so we define current as the direction of the positive charge movement. So in this example, if we put a positive charge here and a negative charge here, we will have a current that flows in this direction. But in order to get the current to flow, we needed to put a charge across this, or two opposite charges across this. So this difference in charge is called voltage. So voltage is actually a potential energy between 2 points that can act on a charge in order to move it. And voltage is defined as the amount of energy, which is in joules, per charge that is available to act on that particular piece of charge. Okay, and so just for reference, or kind of to put it in scale, 1 volt is the potential difference between 2 points that will impact 1 joule of energy per coulomb of charge. So it represents basically energy that we can use to move the charge through a material. Okay. Voltage has a unit of volts, which was, of course, named after another scientist, Alessandro Volta, in the 1700s and 1800s, and he did work on this, electromagnetics, and so they named this unit after him, and so we give it the capital V, which is what we kind of the unit for it, and it's a derived unit, meaning that voltage is defined as energy per charge, or joules per coulomb. And so joules per coulomb is the official kind of units of a volt, but we give it the kind of the shorthand of volts. So when you talk about voltage, the units are volts, so it's just kind of easy to remember. Okay. Now, a voltage source, something that provides a voltage to a circuit, it provides that voltage regardless of whether there's current flowing. So it's kind of interesting. If you have a battery and you measure 9 volts across its terminals, you'll see on the positive side to the negative side, there's a difference of voltage of 9 volts. And there's no current flowing when you make that measurement. But then if you put a circuit in the middle of those and you power, let's say, a light bulb, current will start flowing. And in theory, that battery will still have 9 volts on it. So it's a potential energy that can exist from a source, whether or not you're moving current with it. Okay, so when you apply a voltage to a material, this is an important concept in electrical engineering, or all circuits in general. Current can actually only flow in a loop. Okay, and so that has to do with kind of this regenerative nature of moving electrons and holes around. So you don't have, like, when you build a circuit, you put this material in here, there's only a certain number of electrons that exist. So if you're going to move an electron, one way, you basically have to have another electron take its place, essentially. Okay, so if you looked at this circuit and you said there's, 20 billion electrons in this small little tiny circuit. They're moving in a loop. They're not like all just rushing over to one corner and sitting there. It's like you have to have a loop for them to flow so that you can continually move this current around. Okay, and so in this example, no current would be flowing. You would have a battery, let's say, that had a voltage. It's got its 2 terminals, and we say that the voltage is across those terminals, and there's always a positive part, and there's always a positive terminal, and there's always a negative terminal. terminal. And since this circuit is open, meaning that it's not a closed path, it is not technically a circuit. And you know, a circuit is basically, you can think of it like at the gym where you have a circuit course where you move through each of the elements and then repeat them over and over. So it's essentially a loop. And so if I wanted current to flow in this, what I'd have to do is close the circuit, and now I form a loop. And now this voltage can act upon the materials in order to move the charge through and around the circuit and ultimately move current. And current is what we then use that has this property that we can use to do things like light up something, create heat, or move a motor or something like that. Okay, so those are kind of a couple concepts of just electrical circuits. In terms of magnitudes of voltages used in a society, small, you know, integrated circuits, IC, little chips in computers and stuff, they can be powered anywhere from, you know, half a volt, 0.7 volts, all the way up to maybe 5 volts in kind of modern computers. The trend is that electronics use lower and lower voltages. If you think about like your USB port, that a standard USB on a Windows machine, it outputs 5 volts. Okay, there's sometimes you can have that using that same connector, you'll see like 9 volts in some applications, but we're talking about you know, a handful of volts. Okay, so 5 volts is what charges, you know, your phone. Okay, and that would coming out of a USB port. Your electrical outlet at home, we call this 110 volts. So that's what you see across these two terminals. And here's what's interesting about this. Notice that there's two terminals. The positive and negative parts of this are on these two little slits. So one's positive and one is negative. This is going to be your ground terminal right there. You don't need to, we'll discuss that in a later video. If you look at like a dryer, electric dryer, you're looking at 220 volts. And then if you look at those large transmission lines that you see when you're driving down the interstate, you know, those can be 500,000 volts. So you see this huge range of numbers. Okay, the next electrical concept is what we call power. So one of the things of interest when you build circuits and analyze circuits is the rate of energy being put into or used by a circuit. And this rate is called power. And it's defined as the energy per time, or has a unit of joules, which is energy, per second, which is time. Okay. Now, this is joules per second. Again, we are going to actually have another name for the actual unit, which is called watts. So the unit of power is called watts, and it's a derived unit. It actually just is a shorthand for joules per second. But whenever we talk power, we talk about watts. Okay, now where did watt come from? Well, it's another guy, James Watt. So he was a scientist that was honored by them naming this unit after them. But basically, 1 watt represents a circuit energy rate of 1 joule per 1 second. So it represents like just what is happening in the circuit as this thing operates. Okay, so in electricity, power is actually a very simple equation. What you do is you multiply the current by the voltage. So P is equal to IV. So this is like a very simple equation, and it's very widely used. So it's something you can remember the rest of your life. If you examine kind of the way that this works, you looking at the units of power, if you look at current, remember current was charge per time that passes through a point, which has a unit of coulombs per second. We shorthanded it as an amp, but it's actually coulombs per second. And then if you look at voltage, which is now joules per coulomb, the work you put on this on each charge, then that's what you get when you multiply current times voltage. Well, if you look at what happens with the units, the coulombs actually cancel, and what you're left with is the definition of power, which is joules per second, or 1 watt. So it's a very simple equation that is very powerful. I mean, it is quite easy actually. Is P equals IV, and you got power in an electrical circuit. When it comes to circuits and power, you always have this notion of a source and a load, okay? And so a source is what provides power to a circuit. And so a circuit doesn't do anything without a source, okay? It needs a supply of power. In this graphic right here, the battery would be considered the power source. We also sometimes call it a voltage source because it provides the voltage. That's the energy that it's going to provide for the circuit. There's also current sources, but we can call this a power source, so P source, okay? And then a load, in this case, the graphic shows it as a light bulb. This is the part of the circuit that uses the power, okay? And so the terminology that you use kind of varies. Sometimes we'll say with the power that this is the power source. We source, 1 watt into the circuit. We're sourcing power, okay? And then for the load, what we can say is that the load is consuming power. Sometimes we say it's dissipating power. So you'll hear different words used for it. It all means the same thing. It's like it's taking the power that is sourced by the power source, and it is doing something. So the load can be creating light with an electrical circuit. It can be creating motion. It can be creating heat. It can be communicating information. It can be doing all this sorts of stuff. But circuits don't run unless they have a power source, okay? Now, in theory, in the power that comes in on the source is equal to the power of the load. So we have the left-hand side of this equation means that is the power being sourced. Okay, so this battery is giving that power, and then somebody else is using all that power. So the load is using, that amount of power. So 1 watt in, 1 watt out. Okay, so it's kind of like a conservation of power thing. Sometimes people will talk about, well, isn't there loss in the line on the wires and everything? It's like, yeah, you just lump it all into the power consumption of the load. Okay. All right. So let's again look at the kind of like magnitudes of power usage in society. So your small integrated electronics, your chips that are in your phones and your computers. I mean, these can be, 0.1, half a watt up to maybe 2 watts. Sometimes you'll see like 5 watts for really huge chips, maybe, yeah. So that type of order. Your USB port, again, it's like a standard USB started at about 2 watts. Some of the bigger ones can go up to 3 watts, some of the more advanced standards. But I mean, we're talking just a couple watts. Your outlet at home, remember that the voltage on your outlet is 110 volts, and one outlet could source 15 amps. So if nothing else was plugged into the breaker that it's on. And so if you just multiply those together, you get like 1600 watts. If you think about like your home, it can be like 15,000 watts. And again, that's thinking about like what's the current we looked at. It's like, like 100, 200 amps. The voltage that's coming in is, 110, 220 volts. And so you multiply those together and you're in the tens of thousands of watts. And then finally, when you get to these big transmission lines that you see that are moving power from a generation source like a power plant to cities, I mean, those are carrying 500 million watts. I mean, just huge numbers of power. Okay, so that is voltage and power, and hopefully that gives you a little bit of understanding about the terminology and the concepts. See ya.